The focus of this lesson is on graphing rational functions. So we're going to start off by trying to factor our numerator and denominator of our rational function. So it's not obvious offhand how the numerator factors, but we can use what we learned from 3.4 and 3.5 as far as determining the zeros using our possible rational zeros and synthetic division to help us factor. So this is a little more complicated than what you typically have to do, but just understand this is tools that you're able to use if needed. And so the factors of your constant are plus or minus 1, and the factors of your leading coefficient are plus or minus 1 as well as plus or minus 2. So that means at the end of the day your possible rational zeros are plus or minus 1/2 and 1. So you would do your synthetic division taking into account those. And I'm going to start with the negatives just because I happen to know how this problem plays out. So I'll start off by testing if negative 1/2 is a 0. My leading coefficients of my polynomial are 2, 1. You're missing the 0x term, so put a 0, and then you got your constant of 1. And then do your synthetic division, pull down your leading term. Multiply by -1/2, you'll get -1. Add, you get 0. Multiply by -1/2, you get 0. Add, you get 0. Multiply by -1/2, you get 0. Add, you get 1. So -1/2 is not a 0. So then I move on to -1 using the same coefficients of 2, 1, 0, and 1. Pull down the 2. Times a -1 is -2. Added is -1. Multiply by -1 is 1. Added, you get 1. Multiply by -1 is -1. Added, you get 0. And so we can see that -1 is a 0, which means x plus 1 is a factor. And then the other factor that corresponds is our depressed equation that we got as a result from our synthetic division, which is going to be 1 degree less than our polynomial to begin with, which was degree 3. So it's going to be 2x to the second minus 1x plus 1 is the other factor. And the debate is whether that factor will factor any further, but if you were to do the quadratic formula on it, you would see, in fact we can do it, the opposite of b is 1 plus or minus the square root of b squared would be 1 minus 4, a would be 2, c is 1 all over 2a. We would see that this value under the radicand, the determinant if you will, or discriminant, is negative. And so this is not going to result in a real 0, so that won't factor any further over the real numbers. So k of x in its factored form is going to be x plus 1 times 2x squared minus x plus 1 all over x squared. Notice there are no common factors from numerator to denominator, so we do not have anything to cancel out, so we'll have no wholes, so that's our step 1. As far as our step 2, we need to figure out our x-intercepts or our zeros. Those come from our numerator, so setting each of our factors from our numerator equal to 0. But if we set x plus 1 equal to 0, we can see pretty quickly that if we subtract 1 from both sides, we get x is a -1 as our 0. And then we already decided from using the quadratic formula on 2x squared minus x plus 1 that we do not get any real zeros, so we can skip that part. So that's our zeros, is just x is -1 as far as real zeros go. And then in our denominator, that's where we can determine our vertical asymptotes by setting each factor from the denominator equal to 0. But if we set x squared equal to 0, and we take the square root of both sides, we ultimately get back that x is 0. So that's our vertical asymptote, x equals 0. So we could start to draw the graph if we want to. So we're going to have a vertical asymptote at x equals 0. So I'm just going to draw that in here in blue. And then at x equals -1, we're going to have a 0. So go ahead and plot that 0 at x equals -1. Okay, so then we can go ahead and move on to determining the behavior to the left and right of the 0 and the vertical asymptote. So if we go to the left of the 0, that would put us at -1.1. If we go to the right of -1, which is our 0, that would put us at -0.9, so 1/10 to the right. And then if we go to the left of our vertical asymptote, that'll put us at -0.1, and to the right would be 0.1, so +0.1. So again, trying to determine what the behavior to be. We can look at the factored form here to help us determine signs. If you put in -1.1 for x, for this first factor we would get something negative back if you add 1 to it. And then for the second factor, if we take -1.1 and we square it, that will come out to be positive, and that leading term will rule, so the whole factor would come out to be positive. And then -1.1 squared will come out to be positive. So negative divided by a positive is overall negative. So the behavior to the left of -1 is going to be below the x-axis. And then if we continue on at -0.9, this first factor will be positive, and then -0.9 squared is going to come out to be positive, and then added to the 1 will make that positive overall, so that'll win. And then -0.9 squared will come out to be positive. So positive divided by positive is in fact positive. So the behavior to the right of that 0 is going to be above the x-axis. And then if you do -0.1, you'll get a positive for that first factor, and then -0.1 squared times 2 is going to be positive, added to 1 is going to be positive, subtracted is going to be still positive. So positive overall, and then -0.1 squared is going to be positive. And again, you can always evaluate those values at 2x squared minus x if you're not able to determine that. You can plug that into your calculator if needed. But positive divided by positive will be positive. So to the right, or sorry, to the left of a vertical asymptote, we'll see that we're shooting to positive infinity, which is good because it looks like my graph was going that way anyways. And then at 0.1, the same thing. If you add it to 1, you'll get positive, and then if you square it, add 1, and then subtract it off, you'll still be positive. And 0.1 squared will be positive. So it's positive divided by positive, which is shooting to positive infinity on the right of that 0, since we got a positive overall. So that determines our behavior to the left and right of our vertical asymptote and our zeros. So then we move on to our next step, where we would look for any y-intercepts. So if we want any y-intercepts, we have to let x be 0. So in other words, evaluate our function at 0. So wherever there's an x, put in 0. And we could do the factored form, but it would probably be just as easy as to do the original function. So where there's an x, put in 0 and see what the result is. But if we do that, we would see in the numerator we're left with 1, and in the denominator we're left with 0, but 1 divided by 0 is undefined. And so what this means is that there's no y-intercept. Okay, so there's none. So it's not going to intersect the y-axis, is what this means. So then I would move on to the next step, which would be finding the horizontal or oblique asymptotes So if we look at our function, none of the factors canceled out, and you can see that you have a higher degree in the numerator than the denominator, which means division can occur. Well, then that means you're going to have an oblique asymptote as opposed to a horizontal asymptote. So OA is what I use for oblique. So we will be dealing with an oblique asymptote, and the way you determine that is by doing long division. So I need to take x squared, the denominator, and divide it in my numerator, which is 2x cubed plus x squared plus 0x plus 1. Account for that missing term with a 0 coefficient. 2 times x is the number of times x squared goes into 2x cubed, so it goes in 2x times. 2x times x squared is 2x cubed. So you did the multiplication step, so then you would subtract, and then you would bring down. But if you say you have 0x cubed, that's really just saying you have 0. It's not there. So x squared into x squared goes in one whole time. So multiply by 1 times the x squared, you'll get a positive x squared. Go to subtract, you'll get 0x squared, and you'd bring down the 0x, but that's not going to be anything, so go ahead and bring down the 1. It's as though these terms aren't here, because if you have a 0 coefficient, you're nothing. And then x squared cannot go into 1, so this 1 is your remainder, and you write your remainder over your divisor. So our quotient is 2x plus 1, and then our remainder is 1 over x squared. And then the idea behind an oblique asymptote is as x goes to infinity, then the remainder piece will shoot to 0, because 1 divided by something really large is something very small that approaches 0. And so this piece, the remainder piece, disappears, and all you're left with your quotient. That's your horizontal, or sorry, that is your oblique asymptote. Y equals 2x plus 1, the quotient. And so what you would do is you would go to graph that on your line, or on your rational Cartesian coordinate plane. So the y-intercept is at 1. So this line doesn't actually exist because it's an asymptote, but we're just going to plot the points like it does. And then you would rise to the right 1, since that's your slope, and then fall to the left 1, and then that'll give you that oblique asymptote, which is just a slanted line, if you will. And again, those points don't actually exist. And so then now we can go ahead and draw our graph. We have everything we need. We see that we are going up to the left of our 0, connect that to this 0, and then follow the asymptote down. On this piece, we're going up to the right of the 0. That's fine, just follow your asymptotes around. And that is a rough sketch of the rational function, and that completes our 5-step process, or if you will.